Good morning. We will be starting in 4 minutes. Okay, let's start. Okay, so this week we will start a new topic called generating functions, and then we are going to give a very brief lecture summary now. So in this set of slides, we will be talking about generating functions, and then in particular, we will be using them to relate the combination problem and the permutation problem that we are studying so far. So, okay, so let's see. Okay, so suppose that we have three objects A, B, C, and then we know that there are three ways to select one object from them. So we may either select A, or B, or C. So somehow we can describe this by an expression. We use plus to represent or. So here we may be selecting A, or we may be selecting B, or we may be selecting C. So just read this as some kind of an encryption of what we are saying. So not exactly like a mathematical formula, but it is what we are saying. So we can use A plus B plus C to describe the three ways to select exactly one object from them. And similarly, if we want to describe three ways to select two objects from them, then we can use the expression AB plus BC plus CA. So AB here means that we are selecting two objects, namely A and B. So we use multiply to describe the AND operation. So A and B, or we may select B and C, or we may select C and A. And how about selecting three objects? So to select three objects, there is only one way, and then we can describe it by A times B times C, meaning A and B and C. Now, if we look closer into these terms, A plus B plus C, AB plus BC plus CA, and then ABC, okay, we can actually obtain them by this. Okay, so suppose that we look at this time, this is a mathematical polynomial. 1 plus ax, this term, multiplied with 1 plus bx, and then multiplied with 1 plus cx. Then if we do the expansion, then we have some interesting fact. So we will see that, okay, after the expansion, we will have 1 plus a plus b plus c multiplied with x, and then ab plus bc plus ca, this term multiplied with x squared, and then abc, this term multiplied with x cubed. So these coefficients, so the coefficient of x represents is exactly the representation of the ways that we are selecting one object. The expression for the coefficient for x squared, this one, this is the same as our representation of the ways that we are selecting two objects, and then x cubed. So this is x cubed, and then the corresponding coefficient ABC is the representation of how we are selecting three objects. So x to the power I, where I is equal to 1 or 2 or 3, talks about what we are selecting exactly I objects. So here, x to the power 1, 1 object, x to the power 2, 2 objects, and then x to the power 3, 3 objects. Okay, this is something interesting. So we can actually interpret the original polynomial by using this kind of, so this counting problem or this selection problem can be described by using the rules of sums and products. So in particular, 1 plus ax here, it means that there are two terms here. So there is one way. Okay, so it means that we can select object A or not. Okay, 1 plus ax. 1 here means that we are not selecting A at all, but then ax here we are selecting the object A. So not select object or select A. But here, so we intentionally add an x here because x is something that is useful here. We will see it very soon. We actually see that already, but then we will look at it again. And then the product of the terms 1 plus ax, 1 plus bx, 1 plus cx actually means that when we are doing the selection, we need to make a choice whether we are selecting A or not, whether we are selecting B or not, and whether we are selecting C or not. So once we have made up our mind, then this will give us a particular selection. So the selection is a process that we choose whether we are selecting A or not. So this is the first choice, and the second choice we are selecting B or not, and the third choice we are selecting C or not. So in that case, the whole process can be represented actually by multiplying the corresponding 1 plus ax, 1 plus bx, and 1 plus cx. And why we introduce the x here intentionally? Because when we have an x here, it means that we are selecting things, but when we don't have any x here, we are not selecting anything. So the x power actually talks about how many times we are selecting an object. So if you look at the previous case, so here this is x to the power 1. So when the power is 1, then it corresponds to selecting exactly one object. And here the power of x is 2 here, so x squared. So in that case, we are talking about the ways that we are selecting exactly 2 objects. So the power of x is something that indicates how many objects we have selected. And on the other hand, the coefficient of x to the power k indicates that what are the ways that we are selecting k objects. Okay, so the constant term refers to the case that we are not selecting any object at all. Now, the above example motivates us to use a polynomial to represent a sequence of terms. So in particular, let us look at this polynomial: 1 plus 3x plus 6x squared plus 10x cubed plus 15x4, and so on and so forth. And in fact, when we list out this polynomial, what we really hope is to represent this sequence of numbers 1, 3, 6, 10, and 15. And then what we care here is about which number is at the ith location. We don't care about the x here and the x squared here. The x here, the x squared here, the x cubed here, actually we just want to use it to indicate which term that we are talking about. This is the third term, or this is x to the power 3. Apart from the constant term, this is the third term, starting from the beginning, excluding this one. So in that case, this expression, this polynomial, will help us to generate the terms in the sequence in the order that it appears. And so we call this polynomial a generating function of this sequence. Okay, we use a polynomial to represent a sequence, and then we are interested only in the coefficients. And here, the term x, x squared, x cubed, they are called indicators. Okay. Now, of course, it is not just so there's not just one single way of using indicators. Like x here, we can actually use cosine x, cosine 2x, cosine 3x here, or maybe using something like this falling power, x to the power 1, x to the power 2. So this is the falling power. It means x times x minus 1. x3 falling here means x times x minus 1 times x minus 2. Okay, so we can also use these as indicators, but the most common indicators that we use are x, x squared, x cubed, and so on and so forth. But on the other hand, some of the indicators are not preferred, so maybe we can use indicators of the form like 1 plus x, 1 minus x, and so on and so forth. But then it is not good. It is because we may have two different sequences, but then their polynomial will be the same. Okay, so in that case, it is not good. So in that sense, yeah, so we better multiply the term that we like to store each of them by a different x here. So the constant term is 1, and then the next term is multiplied with x, and then the further term is multiplied with x squared, and so on and so forth, so that we don't mix the numbers in the sequence together. Okay? Okay, so that is what I was just saying. So this is the most common indicators that we are using. So in that sense, we are assuming this throughout this set of slides, and then we will use this function fx, which is equal to a0 plus a1x plus a2x squared, and so on and so forth, to represent this sequence. Okay? Okay, now let us relate generating function with the combination problems that we are studying. So this is what we have introduced at the beginning. So here, the expansion of this expression actually will tell us the specific ways of selecting objects. But what if we are just interested in counting the number of ways of selecting objects? So we don't care whether we are selecting A or B or C only. We just want to to say, oh, there are 3 ways of selecting exactly one object. So it will be very simple. If we are just interested in the number, then we can substitute A, B, C all by 1. So by setting A, B, C to be 1, then we will get this expression, 1 plus 3x plus 3x squared plus x cubed, as the expansion of 1 plus ax times 1 plus bx times 1 plus cx. And the 3 here actually comes from a plus b plus c. So there are 3 ways. This 3 comes from ab plus bc plus ca. So it is 1 times 1 plus 1 times 1 plus 1 times 1. So we get 3 ways. And then here, this is a times b times c, which is equal to 1 now. So there is 1 way. So in that case, by doing the substitution of ABC to be equal to 1 for all of them, then we get a formula for doing the counting. And then this expression generates the different ways of selection of different number of items, such that x to the power k is the number of ways to select exactly k items. Okay, so this is something really interesting, right? So if we are okay with 1 plus x times 1 plus x times 1 plus x here, then we can extend the idea to look at this 1 plus x to the power n. So the intuition of 1 plus x to the power n in the generating function here that we are talking, it talks about we have n objects to select, and then for each object, we can either select it or not. So how many ways to select the objects? How many ways to select one object? How many ways to select 2 objects? And so on and so forth. So in that sense, okay, using our physical understanding, we will see that the coefficient of x to the power 1 corresponds to the number of ways of selecting exactly one object. And by our definition, this is exactly Cn1, n choose 1. This is Cn1 means there are how many ways to select one object out of n objects. So x squared, the coefficient will be n choose 2, x cubed, the coefficient will be n choose 3, and so on and so forth. We know that this is true. We know that this is true just by doing what? Just by having our interpretation of 1 plus x to the power n as a generating function of the selection problem, and the meaning of the coefficient of each of the x to the power k term, so that we write it down here. Okay? So this is actually called the binomial theorem. And then, yeah, so this is something interesting, right? So suppose that, so this is just a sidetrack. So suppose that we know that this is true. 1 plus x to the power n is always equal to, so here, although we don't know what is the formula for Cn1, what is the formula for Cn2, and so on and so forth, we still know that this is true, okay? Of course, we know that now. Yeah, we have derived that already, but even if we do not know what is Cn1, what is Cn2, what is the exact formula for them, then we can still talk about this is true here. And now, suppose that this equation, this identity is known, then we can solve this easily. So we can show that n choose 0 plus n choose 1 plus n choose 2 up to n choose n is equal to 2 to the power n. So this is about summation of a certain row in the Pascal triangle. So how do we get this? Very easy. So this is true, so we substitute x to be 1, then this is this one, okay? And then 1 plus 1 to the power n. When we substitute x to be 1, it is 1 plus 1 to the power n, so which is 2 to the power n, so we get this one. And how about this one? So this is like we have a Pascal triangle, observe a particular row, but this time we are doing alternating. So we add and then subtract and then add and then subtract until the end. So we are going to show that the overall results will be equal to 0. And this is also very simple because let's say this is true, then this time we are substituting x to be minus 1. So that on the left hand side, it becomes 1 minus 1 to the power n, which is 0. And on the right hand side, we will get the alternating terms. Okay, there is one exception actually. There's one exception. So here it is true when n is greater than or equal to 1. But then when n is equal to 0, then it is not true. Yeah, because when n is 0, on the left-hand side, we are talking about 0 to the power 0. So what is the interpretation of this? So it is actually an undefined term. And in this particular case, the right-hand side will be C0, choose 0. And then by definition, this term, we will say it is equal to 1. So this is the exception, the only exception that this formula is not equal to 0. Okay? And how about this one? This time, we have n choose 0 square plus n choose 1 square, and so on and so forth up to n choose n square. We are saying that this is 2n choose n. Now for this one, actually we can show this by, method 2 is more common. So instead of interpreting n choose 0 square as a square of two numbers, let's change it to n choose 0 multiplied with n choose n. We know that this is true because n choose x is always equal to n choose n minus x. So for each term, we are expressing them as something like this. And then somehow we can use a combinatorial argument to show that the value on the left-hand side is exactly equal to the value on the right-hand side. So basically, you can imagine that you have n boys and then n girls, and then we want to select a total of n people out of them. So how many ways are there? So we may be either selecting 0 boys and then n girls, or selecting 1 boy and n minus 1 girl, or 2 boys and n minus 2 girls, and so on and so forth. But then this is basically, I have 2n people, I'm selecting n of them. So in that case, method 2, you can use this as a very easy way to show that this equality is correct. Okay, the next one here is this one. This is something strange, but then I believe you can do it easily by using the hint here. So let's skip this. And then this time, we want to find out what is the coefficient of x to the power 23 in this expression. Now, so first of all, what does this expression mean in the combinatorial sense? So we can think of this as we have 100 types of objects, and then for each object, we may either select 0 of them, or 5 of them, or 9 of them. So for instance, let's say we have 100 types of fruits. So we will be selecting some apples. So apples, when you buy it, either you do not buy it, or you buy it with a bag containing 5 of them, or you buy it with a larger bag that contains 9 of them. Okay, and the same is true for oranges, the same is true for lemons, and so on and so forth. So x to the power 23, the coefficient of x to the power 23 is saying that how many ways that I can buy exactly 23 pieces of fruit. Okay. So this is the meaning here. So, but then you see that, okay, how do you get 23? So based on, because in the end the power of x is 23, so it only comes from x to the power 5 and x to the power 9. And then from 5 and 9, the only way to get 23 is you have 2 9s and then you have 1 5, right? So in that case, actually we are asking the same question, the equivalent question. Out of these 100 types of fruits, I need to select 2 types, exactly 2 types, that I'm buying with a larger bag, and then exactly 1 type that I'm buying with a smaller bag. So I have 2 9s and then 1 5. So the number of ways of doing so is 100 choose 2 multiplied with 98 choose 1, or 100 choose 1 multiplied with 99 choose 2. So both of them are correct. So this is the answer for this question. Okay. And then another one, this is very interesting. So we want to use this one. So let's look at this 1 minus 4x to the power minus 1 over 2. And then we want to find out what is the coefficient of x to the power r in this term. we are claiming that this is going to be 2r choose r. So first of all, how do we get the coefficient of x to the power r in this one? So again, we will rely on the binomial theorem, but this time we have a power which is not a positive integer. So we will have the generalized binomial theorem, or you can use the Taylor's expansion or Maclaurin series, whatever, to do the expansion of this one. And after that, we check what is going on about the coefficient of x to the power r, so that after simplification, you will be able to get 2r choose r. Okay, so this is something that is done in the lecture, so you can go through the lecture recording and then see how this is done. But suppose that this is true. Now, suppose that this is true. So that means what? That means that this particular polynomial, so you can think of this as a polynomial in x, but then with infinite number of terms, because after Taylor's expansion, you will have infinite number of terms. But then this will be the polynomial that helps us to generate the terms C00, C21, C42, C63, and so on and so forth. So this is the generating function of this sequence of numbers. Okay. Now, this is true, right? So let's imagine if we multiply this with itself, what will happen? Now, when we multiply this with itself, we will get 1 minus 4x to the power minus 1. And 1 minus 4x to the power minus 1, it is the generating function of the terms 1, and then 4, and then 4 square, and then 4 cube, and then 4 to the power 4, and so on and so forth. So if we multiply this by itself, then we will get a generating function of 4 to the power k. But this will also, or 4 to the power t here. But on the other hand, if we look at the right-hand side, so in that case, when we notice that this is equal to, so this one is equal to C00 plus C21x plus C42x squared plus C63x cubed, and so on and so forth. When you multiply this by itself, the coefficient of x to the power t term will be on something on the left-hand side. This is the coefficient of x to the power t term. So this is easy, okay? And then this is something that we have when we look at it as a generating function. And then this is what we look at when we, after doing the simplification of 1 minus 4x to the power minus 1 over 2, the square of it becomes 1 minus 4x to the power minus 1. Then after simplification, we see that this is the generating function for 4 to the power t. So after the left-hand side and the right-hand side are the same, so we will have this identity. So this is something that we can obtain, based on the result here. Okay, now, so let's do a little bit more complicated thing. So what is the meaning of the longer, a more complicated expression like this? So we have 1 plus ax plus a squared x squared. This is 1 plus bx, and that is 1 plus cx. So when we multiply this together, we will see that we are talking about, we have the first type object. I may be selecting a, or I may be selecting two of them. So let's say call it a squared. And then for the second type, I can either do not select it or just select one of them. And then for the third one, I can either not select it or select it with one of them. So this is about how many, so if you multiply them together, the coefficient of x to the power k tell us how many ways are there to select exactly k objects. But then this is something a little bit different. This time we have 1 plus ax multiplied with 1 plus a squared x squared instead. So here, what does it mean? It means that, first of all, I will have an option of selecting a or not. And then after that, I will have an option of selecting two a's. A squared means a and a together or not. So then that means that in combination, actually, I will have a choice of selecting one a here and then two a's here. So I can have a cubed. But for here, we don't have this one. So these are two different meaning. Okay, this is just a yeah, just a way to test your understanding. So let us skip this. So this is rather easy. Yeah, so you can go home and then verify this to be correct. And this one, okay, so this one is what? So this one is something, this expression, this polynomial to the power n. Because it is to the power n, that means that we have n types of objects. We have n choice to make. And then for each type, there is one way of selecting nothing. There is one way of selecting one. There's one way of selecting two of them. There is one way of selecting three of them, and so on and so forth. So this corresponds to what? This counts the number of ways to select from n types of objects such that each type you have unlimited supply. So you may be selecting one apple or two apples or three apples or whatever. So there is unlimited supply. And then the coefficient of x to the power k tell us what are all the possible number of ways. So what is the number of ways that we are selecting exactly k items such that altogether there are n types, and then for each type there is unlimited supply. Okay? And then notice that this 1 plus x squared up to this infinity, it is exactly the same as 1 minus x to the power minus 1. Okay, so because of this whole thing to the power n is equal to 1 minus x to the power minus n. Is that okay? And then by using this binomial expansion, so we know that the x term, okay, after the expansion, we will have c minus n choose 1 multiply with minus x plus c minus n choose 2 multiply with minus x squared, and so on and so forth. And then what is the notation here? Minus n choose 1 or minus n choose 2. So this is a shorthand notation for what? For you start with minus n. So minus n choose r. This term, minus n choose r, is what? So minus n choose r is simply minus n to the falling power of r. So you start with minus n and then you take r terms. Each term is one less than the previous one. You get the product of them and divide it by r factorial. Okay, so this is c minus n r. So this is minus n falling power of r divided by r factorial. Now, if you look at this one, so c minus n 1, you will be multiplying with minus 1. C minus n2, you will be multiplying with minus 1 squared. So if you want to look at the coefficients of x to the power r, so this is the coefficient of x to the power r. So this will be exactly equal to minus n to the power r falling multiply with minus 1 to the power r divided by r factorial. Is that okay? And as we can see, all the minus here will be cancelling with each other. So in that case, this value is the same as this value. So this is taking absolute value sign. And then so we see that we don't need to care about the minus. So we care about what are the terms that we are multiplying in this numerator. So in this numerator, the first term is minus n, and then the next term is minus of n and then minus 1. So minus of bracket n plus 1. So in that case, so this is like minus n to the power r falling. But on the other hand, if you forget about the minus term, because they are going to be cancelled, it is going to be n to the power r rising. You start with n and then you get r terms. Each term is 1 greater than the previous one, rising. So n to the power rising r. And in that case, n to the power r rising is the same as n plus r minus 1 to the power r falling. And then after conversion, we will see that this is exactly cn plus r minus 1, choose r. Okay, so we get an equality. This term is actually this term. And what does that mean? It means that the coefficient of x to the power r is exactly n plus r minus 1, choose r. What was the coefficient of x to the power r? This corresponds to I have r objects to be selected. Out of n types, each type it has unlimited supply. So we have solved exactly the same problem before. This is like we have R balls, we have n minus 1 sticks, and then counting the number of permutations of them. So it will be R balls plus n minus 1 stick, and then I choose the R positions to put the balls. So it is exactly n plus R minus 1 choose R. Okay. And then we have another example. So this time, instead of starting from 1 plus so on and so forth, we start from x to the power q, and then x to the power q plus 1, and so on and so forth, up to x to the power q plus z minus 1. And then this term multiplied by itself n times. So the meaning of this one is also simple. So we have n types of objects. For each type, we may be selecting q of them, or q plus 1 of them, or q plus 2 of them, up to q plus z minus 1 of them. And then the coefficients of x to the power k tell us how many ways are there of this selection such that the total number of objects is k. Okay, and then we can use this idea to solve the problem here. So let's take a look at this problem. So we have 4 persons. Each one of them is rolling a die, and then we want to ask, so each one of them has their own die. Okay, so different colors. Okay, but then we are counting how many of ways are there, so that the total value that we see in the outcome will be exactly 17. So this time each one will have a die, so that it will have one way to produce a score of 1, one way to produce a score of 2, and so on and so forth, and one way to produce a score of 6. So in that case, in that case what? In that case, the generating function that we are looking at will be x plus x squared plus x cubed up to x to the power 6, this term to the power 4, because there are 4 people. And after simplification, so this will become the same as what? Yeah, as this one. This is, yeah, so this is 1 minus x to the power 6 divided by 1 minus x. So this is a term related to what we were talking about. So you can go through the, again, the lecture recording and see. Okay, so when we are doing the counting here, we will find out that the binomial theorem is very useful, because we are, in the end, based on this expression and this expression, and use a combination of them. So this is a combination of them together, so that we can find out the number of ways by using a very, this is a rather simple formula to capture all the things that we want to count. So we don't need to count it by brute force. So there are only a few terms to calculate. Okay, so that's the end for this set of slides, and then we will still have some time. So this week's progress will also include lecture 4, the first 12 pages. Okay, so let's take a look of this one. Now the discussion so far here is about generating functions for counting problems in combinations. But then let's see what will happen if we try to use the same idea for doing permutations. We will see that we will hit a problem. Okay, so this time we are looking at permutations. So to begin with, suppose that we have 2 objects, A, B, and then we see that there are 2 ways to obtain one object and make the arrangement. So this is captured by the expression A plus B. And then we will see that if we want to select 2 objects and then make arrangements, then there are 2 ways. We may have A first, B after that, or we may have B first, A after that. So we can describe this by this expression AB plus BA. But then, so if you use generating function idea, so a possible generating function will look like this. 1 plus A plus B multiplied with x plus AB plus BA multiplied with x squared. And after simplification, we get this one. But then, somehow, by doing so, the distinct permutation of AB and BA will not be recognized here. So they are actually merged into the same term. And then also there is a problem. We cannot simply use the same idea of rule of product and rule of sum to help us to simplify this polynomial or this expression into the product of the case for A and the product for the case of B. Okay, as another example, so this time, so previously we talked about generating functions of Cn0, Cn1, Cn2 up to Cnn. And similarly, we hope to get some generating function for the permutation problem. So suppose that we want to get fx is equal to Pn0 plus Pn1x plus Pn2x squared and so on and so forth. But there is a problem. There is no closed form expression for this fx. Unlike the combinatorial combination case, we get this to be 1 plus x to the power n. Somehow, we still want to have rule of thumb, rule of product going on, and then we still want to have some kind of generating function, but then we don't have this directly. But luckily, we will see something interesting here. Okay, so the first part is the generating function for the CNR terms, but then CNR terms is related to PNR terms. So PN1, when it is divided by 1 factorial, we get CN1. And then Pn2, when it is divided by 2 factorial, we get Cn2, and so on and so forth. And somehow, 1 plus x to the power n corresponds to the way of making n decisions. Whether we choose the first object or not, whether we choose the second object or not, and so on and so forth. So somehow, we see that if we modify the definition of a generating function, then perhaps there is a chance that we can still use rule of product. We can still use 1 plus x to the power n to somehow represent some kind of generating function for these permutation terms. So this motivates actually this new type of generating function. So if I want to generate the term, so let's say this is a sequence that I want to represent, A0, A1, A2 up to AN. But then instead of multiplying A0 with 1, A1 with x, A2 with x squared, and so on and so forth, we are going to multiply AR, okay, with x to the power r divided by r factorial. Is that okay? So the term of x to the power r, it is not the coefficient of x to the power r. It is now not representing the original term AR, but it is representing a modified term, AR divided by R factorial. Is that okay? And then we will call this an exponential generating function of the sequence. So this fx is called the exponential generating function for this one. And somehow we will see that exponential generating function is exactly what we want for doing counting in the permutation problem. So for instance, let's double check our understanding. We just see the example, 1 plus x to the power n. It is exactly the exponential generating function for this one. Okay, so what does that mean? Okay, the coefficient of x to the power r is exactly the same as the r term here divided by r factorial. Is that okay? And similarly, e to the power x. So what is e to the power x? If we expand it, it is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on and so forth. And then this will be the exponential generating function for 1, 1, 1, 1, 1, 1, 1. Okay. And then interestingly, this one is the exponential generating function of this very strange term. So the first term is 1, and then the next term is 1 times 3, and then 135, and then 1357, and so on and so forth. Okay, so this is the definition of exponential generating function. So we haven't talked about the property. So the property is this one, okay. So the exponential generating function can be combined with rule of sum and rule of product. So rule of thumb here, each of these expression talks about the number of ways. This is the exponential generating function for one particular object. So for a certain object, there is one way of choosing it and one way of not choosing it. One way of choosing it and one way of not choosing it. Okay, so we have the exponential generating function of one object, and then by multiplying the exponential generating function of the individual objects that we take into account, so we get rule of product, right? So we will get the exponential generating function of the whole system. Okay, so when we have the choice to do the selection and arrangement that involves n distinct objects, then we don't need to worry anymore. We get what is the exponential generating function for the first object, and then what is the exponential generating function for the second object, and so on and so forth. We multiply them together. Then this will become the exponential generating function for n distinct objects, such that the coefficient of x to the power r is exactly the term that we want when it is divided by r factorial. Okay? And this is actually the example that you can motivate. So this is actually an example to convince you why this is correct. So suppose that here we have p objects of the same kind, and then the corresponding exponential generating function. So here, p objects of the same kind, and then we can select any number of them out of these p objects. Okay, so we know that the number of ways of selecting 0 object, there is one way. The number of ways of selecting 2 objects, there is only one way. At 1 object, there is one way. 2 objects, one way, and so on and so forth. So the corresponding exponential generating function for this particular type of object is 1 plus x squared over 2 factorial up to xp divided by p factorial. And now, what we want to claim here is that suppose that we now have 2 kinds of objects. One has p of them. So we can select any number from 0 to p. And then we have another one, there are q of them. We can select any number from 0 to q. And then what we can do is, after the selection, we can make arrangement. So we want to do the permutation. So how many permutations are there? So the corresponding EGF will be, we have the EGF for the first type of object multiplied with the EGF of the second type of object. So after doing this multiplication, yeah, we will see that this is exactly the number of ways of doing the permutations with these two types of objects. And then, yeah, this is a particular example. So let's say p is equal to 2, and then q is equal to 3. So this is the case for p is equal to 2. This is the case for p is equal to 3. And then we will get something like this. 1 plus this number times x, plus this number times x squared, plus this number times x cubed, and so on and so forth. So as a particular example, the number of ways to select 3 objects out of them and do permutations will be this term, and then we need to multiply 3 factorial back, because this is not the original term. This is the original term after division by 3 factorial. So instead of getting this term, we need to get back the original term by multiplying with 3 factorial. So the number of ways to select 3 objects out of this setting, there are 3 factorial divided by 1 factorial 2 factorial plus 3 factorial divided by 2 factorial 1 factorial plus 3 factorial divided by 3 factorial. And this agrees in exactly what we were studying before, because we can say that, okay, the number of ways of doing so is we may be selecting 2 objects from P, and then 1 object from Q, okay, 2, 1, or 1 object from P and 2 objects from Q, and then 0 object from P and then 3 objects from Q. Okay, and then the corresponding arrangement is 3 factorial divided by this term, this term, and this term. Is that okay? And then you can also revisit the earlier example that we have studied in the in combination and permutation. We have the 5 dots and 8 dashes problem, right? So this is the case where P is equal to 5 and then Q is equal to 8. And then this is for a particular case, a special case. So by interpreting this one, not just 1, 1, 1, 1, 1, but the number of ways of doing selection of one object, number of ways of doing selection of two objects, and so on and so forth, we get the general case where the exponential generating function of a system is equal to the product of the exponential generating functions of each individual subsystem. Okay, so here we have a system that involves two types of objects. So what we can do here is we get the subsystem. So this is for a particular object, this is for another object, and then we multiply them together. This will give us the EGF of the whole system. Okay, so that's all for today. So I'm really, speaking very quickly. So don't worry if you find it fast. So you can always pause and then think, and then always go back to the OCW recordings and then see the details. Okay, and if you have any questions, please send us a question through the questionnaire form, and then we will answer your questions as our earliest convenience, or we will put it in the tutorial and then talk about it then. Okay, that's all for today. Thank you very much. So let me check a little bit, see if you are asking me any quick question here. Let me see. Oh, okay. Oh, so probably. Thanks a lot. So I think that's all. So see you next week. Bye bye.